Okay, well, I'll start now. So, in the first two lectures, which were on last Thursday, I did quite a bunch of, gave you quite a bunch of formal definitions, and it's difficult to expect that everyone remembers them by heart. I often forget them. So, I'll need to remind all of us of some of it. And so there were two things we did essentially. One was to define all the properties of space-time that we'll really need. Uh, Chronological future and past, causal future and past, geodesic like space like null, the causal diamond, which will feature today. And when I use them, I'll remind you what these things are. And then eventually globally hyperbolic space-times. And that was all, I think, what I did in the first half of Thursday. And then we started to analyze actual gravity, and we derived the Raychaudhuri equations. So let me continue from where I stopped last time, which was the derivation of Raychaudhuri equations. And what I'll do is just to very quickly run through the key steps in this derivation, because I was told it might have gone too fast. So I'll just make a list of the key steps. I have provided notes, quite detailed notes, which I think Damian is supposed to upload, or maybe has. They're already there. Unfortunately, every single day I find new errors in them, and I keep sending him new versions. I'm not sure how soon he'll get sick of this, but I'll keep doing that. Okay, so the first step is to actually define a particularly convenient form of the space-time metric. So, and this is to use coordinates called synchronous coordinates. And these are coordinates in which the metric of a quite general space-time can be written thus. So they satisfy four conditions. G00 is -1 and G0I are 0 for all x and t. So everywhere these conditions are true. There are four functions, and intuitively it's not hard to believe that we can achieve this at least in some sufficiently local region by a choice of good coordinates, because there are four functions and we have four choices of coordinates. So we could hope to do this. Last time I went into detail about how this is actually done. I won't repeat that. So you can take this, you can assume we've chosen these coordinates, and in these coordinates we have a very nice identity for the 0, 0, or the time component of the Ricci tensor, and it says that this is -1/2 GIK G dot IK minus a quarter GIK G dot JK GJ L G dot IL. And roughly this is the trace of G inverse G dot, and this is the trace of G inverse G dot squared. So this is an identity. The Riemann tensor is a function of the metric and its derivatives. And if we choose these nice coordinates, then the function is nice, and that's what it is. That really simplifies it. Many of the terms we would have had in R are simply set to 0 by this good choice of coordinates. And now we define theta. Oops, I think I forgot something. Yep, I forgot something. This is del by del 0 of that. So if you look at this, both terms have two time derivatives, one here, and in this case one here and one here. And that's how it should be. because all components of the Riemann tensor are second derivatives of the metric or first derivatives. Good. And so now we define the expansion, and it's our key player in this story of singularities. And this thing is exactly half GIK, G dot IK. So it's the thing that appears in there. And why is this interesting? Well, it's also equal to a half the determinant inverse times the time derivative of the determinant of the 3 metric, this one Gij, and if this starts to diverge or go to 0, it's a signal that something is going wrong with the determinant of the metric. It's going diverging or going to 0, and that tells us that local volumes of space as we are propagate in time are shrinking or separating, and that's exactly the focusing effect we're looking for. Okay. And this other quantity is related to something called the shear sigma, and in the end we find that this equation can, by writing everything, well, by just rewriting this, we get an equation for theta dot, because in fact this is theta dot. This is theta in here with the half, and then there's a minus and a dot, so it's minus theta dot. We bring it to the other side, everything else comes that side, and we find that this is minus 1 by d over d minus 1 theta squared minus, so d is the space-time dimension, then minus trace of sigma squared, where sigma is the shear. That's roughly this, but there's a little extra term in the definition of shear which leads to this also coming out, and finally minus R00. Now this equation contains no dynamics whatsoever. It's just an identity among quantities that arise in Einstein's gravity. Okay, everything is defined in terms of the metric G and its derivatives, and that's the equation. And this is definitely not what Raychaudhuri would have called his equation. It's also not what Hawking called his equation, but it is what Wald calls the Raychaudhuri equation. So Wald and Wald's numerous followers, because Wald essentially wrote the most influential textbook on this field, tend to refer to this as the Raychaudhuri equation. It's just a matter of emphasis. If you're working with general relativity, then of course R00 can be written in terms of the stress tensor and the cosmological constant. And so what Raychaudhuri assumed, what he meant to be his equation and what also Hawking refers to as his equation, is this equation with R replaced by its by the stress tensor, by using Einstein's equations. So Einstein's equations haven't been used here, and if we use them, then the equation that I've just written turns into theta dot is minus a half minus this. Oh, also Raychaudhuri of course worked with d equals 4, as did many people after that, but the derivation is equally simple in all dimensions, so it might as well be general. And now we have 8 pi g t hat 0 0, so t hat 0 0 is t 0 0, where t is the stress tensor, minus a trace term, and then there's the cosmological contribution. And so this is also the Raychaudhuri equation, except after Einstein's equations. And now we see that this is a negative definite term, this is a negative definite term. This is negative if t hat is greater than or equal to 0, then this is negative semi-definite, and this is called the strong energy condition. And this is in some sense the first time we have occasion to worry about such conditions, which in fact have come to dominate discussions of gravity in modern times, because we consider many more generalized theories of gravity, such as string theory or whatever, and we keep having to ask questions about the stress tensor. It plays a role in quantum entanglement, in ADS CFT, and so on. So we are going to assume this. And this is a slight spoiler, because if lambda, this is the cosmological constant, and if it's positive, then it stops, in principle, it stops the right hand side from being negative definite. But we just assume that either lambda is negative, which is not what we believe in our world, or sufficiently small. Relative to these other terms, under these conditions, theta dot is less than 0. Not only theta dot is less than 0, but theta dot plus 1 by d minus 1 theta squared is still less than 0. And this is the bound following from Raychaudhuri equation, which enables us to ask what's happening to space-time in the future or past of an initial value surface. So if this is my initial value surface sigma, I haven't yet said it's a Cauchy hypersurface, and yes, please.
So how it looks in dimension 2?
Dimension 2. Yeah, well, the cosmological term, I guess, just isn't there. It's just a total derivative. So there's no such term, yeah. Yeah, because it's just integral root gr, which is the Euler characteristic of the two-dimensional space in Euclidean. And yeah, so we should really take this seriously for 3 onwards. So, yeah.
Okay, to ask you a question. So when thermal proximity goes to 0, in other words, it means that eigenvalue 1 eigenvalue goes to 0.
Yes.
In other words, it means changing to the signature of space-time. And I wonder what's the status of looking for when physics considers solutions with maybe with local changing of signature.
Yeah, people do worry about change of signature, but I think here that's, so the interpretation of what G going to 0 means will come in a few minutes. I haven't actually given any interpretation yet for physics. The only interpretation so far is that geodesics, which come out from here, under the assumption that theta 0, which is defined on this surface, is everywhere positive, then geodesics will meet each other because the local volume separating these is going to 0. So when det G goes to 0, two geodesics which are separated by a distance of order det G will meet. And the important consequence we'll use is that neither of these can be to still be a geodesic. Yeah. Yeah.
We can see in principle solution is changing for signature.
Yes.
What it should come as extra restriction. So we are looking for solutions.
Yes. Yes, I think that's correct. I think we're looking for solutions with a fixed signature. Yes, I believe so. But I think that's a very interesting question. And in fact, solutions with some kind of signature have been there in work of Hawking and so on, who has matched Euclidean signature spaces to Lorentzian signature spacetimes and talked about the Hartle-Hawking wave function and all that. But in this kind of discussion, no, we assume a signature minus plus plus plus. So actually, the very first definition I gave was of space-time, and space-time is a differentiable manifold with a causal structure, so it has a sense of future and past, and it has a signature minus and then all plus.
And also when the two geodesics meet at a point,
yeah.
just the bent coordinate joins? Or
Yeah, exactly.
really
Exactly. So we don't know that yet, and this is what we'll do in the first part of today's lecture, which is really now. So once I finish reviewing a few things, I will address exactly that question. And just for historical context, the question sort of remained hanging from 1955 when Raychaudhuri wrote his paper to 1965 or 66 when Hawking wrote his paper. So there was 10 years during which this question was just not answered. Okay. And now we understand also why it wasn't answered, because we didn't have the complete technology to understand what sort of spacetimes we want to work with. And we'll come to that in a second. Okay. So theta 0, which is theta at of x and t equals 0, if it's everywhere positive on sigma, then all geodesics focus in the future. I can I'll just justify this by solving this equation in a this bound in a second. But we can also say that if it's everywhere less than 0, then it becomes the past. So you can just flip this diagram and have all the geodesics focusing in the past. And once geodesics focus, then at least those geodesics cannot be continued to be geodesics in the sense that they don't maximize the proper time anymore. Okay. Okay. So let's see what is the conclusion of what is the, how do we integrate this equation. So from this equation, and this was the last thing I wrote last time, we get the easiest way to write it is theta inverse, that's 1 upon theta as a function of time, is greater than or equal to this initial theta inverse plus 1 over d minus 1 into t. And this tells us that if, good, what does it tell us? Uh, ah, sorry, I think I blew this, sorry, excuse me. So what I'm about to show you is that if this is everywhere negative, then they focus in the future, and if it's everywhere positive, they focus in the past. It's not hard to remember, because when theta is positive, it means we have a positive expansion. That means in the future they diverge. That's why it's called the expansion rather than the contraction. So the logic here is that if they're diverging, the geodesics are going further apart in the future, then they must be coming together in the past. Many, as I said last time repeatedly, many symmetrical models of the universe like FRW exactly have this feature. The question was, is it true without symmetry? And that's what this whole analysis is for. Okay. Now, so if this is negative, you see that after a sufficient amount of time, which is in fact t equals d minus 1 upon theta 0, all geodesics have focused. So this is an important time scale. It says given the value of theta on this initial surface, all geodesics will have focused by a time scale of this order. Theta has dimensions of inverse time, so 1 over theta has dimensions of time, and that's exactly what this time means. Now, what you should do if you want to consider focusing this is in the future. If theta 0 is negative. If you want theta 0 to be positive, you actually then also need to reverse the inequality. You need to do things a little differently. From the beginning, just take your time flowing towards the past. Okay. It gets very confusing if you start to manipulate this equation because the inequality seems to go the wrong way. But if you just start by reversing the direction of time, then you will get an analogous equation for time flowing backwards, and then if theta is 0 is positive, then all geodesics will have focused in the past. In any case, all our considerations are future past symmetric, so we never need to prove something again for the past if it's true for the future.
So,
yes.
To derive this equation, you already shown away some of the negative terms in the theta dot equation.
Yes.
Right?
So it's a bound.
So
yeah.
it's already you reached in, like the focusing already happens
yes.
earlier than the time.
Absolutely. Okay. Thank you. By the time. Exactly. And so if we just think of future focusing, and this is my time t focusing, then different geodesics will focus, but no geodesic will reach here. Okay. Now it looks bad, and it would be bad, except that we haven't really got so far any theorem, at least in Raychaudhuri's time, that geodesics should reach arbitrarily far, or what happens if they don't. And we also have no idea whether this choice of synchronous coordinates is the thing that has visited this disaster on us. Maybe that's what it is. And there was a fairly influential paper by people with very well known people. This pair of authors, Lifshitz and Khalatnikov, actually revisited the Raychaudhuri and Komar argument, which is this argument, in the early 60s, and gave a reasoning which I think amounts to a genericity reasoning, saying, look, this is all just choice of coordinates. If you do anything, if you wiggle things, if you just don't choose these coordinates, singularities are never going to happen. So there was actually very concrete published, and it's a long paper. In an era when most papers were 3 or 5 pages long, this was a rather long paper claiming this, and Hawking explicitly cites this as a motivation to revisit the issue. And basically what he says is, we're not going to make vague assumptions, we are going to use heavy duty mathematics, define everything, and state a theorem about what are the conditions under which this kind of focusing predicts some sort of disaster. Which he,
was sufficiently senior
hmm.
he had the ability to get a typist to deal with a paper longer than the usual 2 pages.
I see.
So I see. About the troubles they had getting anything more than 2 pages
typed. I see. I see. I also have a very entertaining story about Khalatnikov, who gave a after-dinner speech at a conference in 1988 that I attended, but it's an incredibly vulgar story, so I won't tell it here. If after a sufficient number of drinks, I'm willing to tell a sufficiently small number of people. Okay, now, so I hope this is all established, and now we are going to come to Hawking in 1966. But before we can really do that, I need to repeat some of the important things I said last time about globally hyperbolic spacetimes. That's the key. That wasn't a fact for Raychaudhuri. It wasn't a fact for these people, because this whole concept hadn't really taken root. It was there in some embryonic form, but it hadn't really taken root, and so people could not rely on it to derive stuff. So let me repeat briefly. Actually, you'll find this quite amazing. So Raychaudhuri equations take a little time to derive. Global hyperbolicity and its consequences takes a lot of time to derive. Once you have both, Hawking's singularity theorem is one line. It literally doesn't even need a proof. Of course, he had many theorems, so the first one, if you like, the one, is almost trivialized. So let me backtrack and remind you that there were 3 definitions of global hyperbolicity. Of space-time. And one from 1953 was the Leray definition, which says that if I have a point P and another point Q in its causal future, then the space CPQ of causal curves from P to Q is compact. In a topology where the open sets are found by looking at the open sets of the manifold and then looking at all curves that are from P to Q that fit in one particular open set, and then saying that set of curves is an open set in the space of curves. Okay. Now there's something there's something appealing about this, because the space of causal curves being compact as a consequence, I mean, what does it really mean? Why did he even get there? It means that if I have this point and this point, and I have a bunch of curves that get there, all of which are either time-like or null everywhere, and I take a sequence of them, an infinite sequence, then there'll be something at the end of that sequence, which will be the, badly drawn, which will be the limiting curve of all those curves. So that's sequential compactness. Technically it says if I have an infinite sequence of objects, then there's a subsequence that in the topology is arbitrarily close to a limit which is contained in the set. So this. And as Gerosh puts it, this means that there are no holes, or what was the exact language? It's very nice. I'll never find it now. Gerosh in 1970, so that's quite a leap from 53, and that's really when this stuff started to become more seriously understood. Um, so yeah, I forgot what I was trying to say. Yeah, so Gerosh, I'll come to the Gerosh definition. I was trying to say something about Gerosh, but never mind. Yeah, I was trying to quote his beautiful statement. That is right. Yep, I told you I'd never find it, so I'll let you know when I find it. Good. So this is definition 1. Now definition 2, it's not really in time ordered, but this is Gerosh, 1970, and this is the statement that there exists a Cauchy hypersurface through which all inextendable causal curves pass. Now this is Gerosh's definition, and this is also our definition for the rest of my lectures. But actually what Gerosh did in this paper was to say, look, this is Leray's definition. I'm going to prove that if this is true if and only if this is true. But this is a much simpler statement conceptually, and therefore I'm just going to use this henceforth as the definition. So it's sort of the most popular definition because it really requires very little to explain. Because well, you have some achronal surface, and then every causal curve must pass through it, either going to the past or to the future, And if there is such a Cauchy hypersurface, then the whole spacetime is called globally hyperbolic. And why is it good? Because then on this initial surface, it really is the existence of a good initial surface, because now I can start my evolving my system with some boundary initial value, some initial conditions, and then wherever I go in the future along any causal curve, my initial conditions will propagate by solving a differential equation, and that's what we want. Okay. What's not a globally hyperbolic spacetime in this definition is when I can have a curve like this, which doesn't pass through here, but also but still is inextendable. You see, you can't cheat this definition by saying, well, I'm drawing a curve here which happens to end here. Tough luck, it didn't pass through your Cauchy surface. A curve which just ends there is called extendable. And if it's extendable, I have to extend it. So if I refuse to extend it, that's just rude on my part. It's not the fault of the Cauchy hypersurface. That's sort of the concept. Okay. But if this point was missing from the manifold, then this curve, which ends here in the topological sense, is now inextendable. And so with this point missing, this really isn't a Cauchy hypersurface anymore. And now what happens is, if I'm here and I have some initial conditions and they propagate up to there, then they go boom and they cannot influence the future beyond that point. And that's when you have an ill-defined initial value problem. So that's the motivation of this definition. And what I'll do in a moment is to give you a sketch of an argument why this definition implies this property. Once we pick this to be our definition, then that's a property which can be derived. And there's the third definition, which actually is intermediate in terms of history. This is Hawking and Ellis. And this is probably around 1960 something, so it's before this. And they said that if I have a point Q in the causal future of P, then I will draw the causal diamond, which is the intersection of the future light cone of P and the past light cone of Q, or the domain of the causal future of this with the causal past of that. And this space we call dpq, and it's called the domain of dependence. Again, if you're going to study anything that people do nowadays with islands or entanglement or anything else, domains of dependence are all over the place, so it's good to know once and for all what it is. And the definition of global hyperbolicity is dpq is compact. So here and there we have compactness entering, but it's different because here we have a very relatively simple, conceptually simple concept of compactness, because this is a space of points, and we know what a space of points, a compact one, looks like. It should be closed and bounded. Okay, this and it's a metric space. So this, on the other hand, is an infinite dimensional space because it's a space of curves. The space of curves is a much harder thing. It's analogous to studying space of loops or whatever. And then the statement that this is compact is apparently harder, but it turns out that any of these implies both of the others, and it's up to you to choose which one is good. And I'll just argue that this implies this, and then we'll find a very important consequence of this. And once we find that, we will go back to the Raychaudhuri equations and show and state Hawking's first theorem. Is that strategy okay? Yeah. Any questions? Yeah. Good. So to understand, so the first thing to understand is that if causal was not in this definition, then the space is not compact. That's already a fact. And for that, I'll give you an example. Let's take a point here, x and t, 1, and let's x and 0, and let's take a point here which is x and 1. So time from 0 to 1, and let's look at curves which go from here to here. Now, the simplest one is the constant. It just stays here for all time. So, this is it. Another one I can think of is this, a sine curve but put sideways. So, this is sine 2 pi t. So, x is equal to sine 2 pi t, right, or pi t maybe, or 2 pi, 2 pi. I could just consider pi. So, now notice that this is not causal because this curve, it's vertical here, so it's causal here, but here it's at 45 degrees and here it's horizontal, which is space-like, it's not causal at all. Now I can generalize this to sine of pi nt, and I'll get a set of curves which do this. So you agree that this is x equals sine pi nt. I think I've just spoilt everything by, no, this was correct. X and t equals 0, and this was x and t. No, I was right. Okay, so time is upwards. Good. Now you can see that this set family of curves for all n has no limit as n goes to infinity. It just becomes nastier and nastier. They just oscillate a zillion times before reaching there. So this is a family of curves which is not does not tend to any. It's a sequence of curves that doesn't tend to any limit curve. But happily we don't care because we are restricted to causal curves, and that sequence, none of the members of that sequence is in the family of causal curves. So it's only causal curves that are claimed to form a compact space. Good. For small n it may be causal. No, even for n equals 1, we just looked at it. For n equals 1, it's just this.
No, it's not the problematic reason.
Sorry? Okay. I see. Yeah, sorry. Maybe I drew it wrong. No. What did I do? It's never going to. So you're saying it's all. This is causal, maybe?
It starts at 45 degrees.
Yeah.
And you did it at 90 degrees.
My mistake. This. Okay. So you're saying this. Where? Okay. Very good. I can probably fix that with something else. But, why did I think it's sine? For large n, it does become steeper. Very good. So that's all we need then. So maybe the first few are causal. Yeah, you're right. So sine pi nt. Yeah, exactly. So yeah, okay. Fair enough. Fine. Okay, which is 1. So it can't be exactly. Yeah. Anyway, I think you get the point. So that's not the set we are worried about. The set we are worried about are causal. Now, to prove this, so I'm not going to give the rigorous proof, which is in any case very long, but we can give a sort of semi-intuitive proof in 3 steps. So the first step is to make a couple of definitions. So one definition is that, let's say I have a family of curves. So I'll fix a P and a Q, and I'll imagine there's a family, and I'll pick a point here that I very unfortunately called, okay, so let me call this point R, and we'll say R is a convergence point of the family. So this is the family of curves. So let's call the curves x n of t of tau, where tau is the proper time, and the convergence, it's a convergence point of the family if every open set around R contains all intersects xn mu of t for n greater than n. So these are things where it's much easier to explain in a picture than in words. So I have a family x mu 1, x mu 2, x mu 3. These are these curves that are coming this way. And if they become sufficiently close packed that every open set around R contains or intersects all these curves once the label n crosses some finite value. So after this point, all the remaining curves intersect every open set around R. Okay, that defines it to be a convergence point. Now there's a different definition called limit point, which says that an infinite subset of curves beyond n greater than n is in this open set. There's a subtle difference, but convergence point is stronger and it's good for us. So this is the first observation. So is this one clear? Is just a point of the manifold whose every open set intersects the family. It's an infinite family of curves. Starts to intersect the family after possibly finitely many curves that lie outside, and then for all the remaining curves, they all pass through this. So this is a convergence point. The second definition is a convergence curve. And the idea is to just recycle the first definition. So now we actually want to define a curve that's a convergence curve of this family, and we say that it is a x mu of tau is a convergence curve if every point on it is a convergence point. So if I claim that this thing is a convergence curve, then I just pick an arbitrary point on it, call it R, look at an arbitrary open set around it. I find that it intersects with this family of curves for sufficiently large n. That's a convergence point. I do that for every point along this particular curve. If it's always true, then that curve is a convergence curve. Okay. Now we are almost there. One lemma and then a theorem. So this is a constructive one. Now, by the way, till now, so far I haven't said anything about being causal or inextendable or any other thing. Now I'll start to use that. So if, now it's a lemma if you like. If xn mu of tau is an inextendable, so it's a family rather of future inextendable, so it's a sequence of future inextendable causal curves having a convergence point as per this definition. Then there exists, this is very powerful, there exists a curve x mu of tau which is all the same properties, future, inextendable and causal, and is a convergence curve of the original sequence. In other words, it's enough for a sequence of future inextendable causal curves to have one convergence point for them to then have necessarily a full convergence curve. It's pretty strong, right? Because having one convergence point you could imagine is okay, but just the existence of that one point guarantees the existence of an entire convergence curve, and the proof of this theorem is based on constructing that curve given that point. Now, it's very difficult to judge whether how much one should go into this proof or not. What's the audience opinion? It's not very long, but you know, it's going to drag things. On the other hand, if you want to believe this, you'll believe anything I say, then I don't need to prove anything. So you know, this is the problem with this field of physics. I think I should say a few words about the proof. So let me start with my causal family, and let's assume that they all have a convergence point R here. Right now, I don't have to assume that they begin or end anywhere. They could just be inextendable. And let's assume that there's one convergence point, R. Now, the proof, as detailed in Wald's book, for example, I think it's due to Gerosh originally, is to draw this open set. So we are given that every open set must intersect all these things. That's what R being convergence point means. But now I draw a very specific kind of open set. So I pass to Riemann normal coordinates, which means I flatten the manifold in a small region around my point. Okay, so I go to Riemann normal coordinates. And once I have these coordinates, then I convert them, I think of them as Euclidean coordinates, and I draw a Euclidean ball. So this sphere is really now not just any open set, but it's a Euclidean ball of some radius r. Now, by the definition of convergence point, all these curves after a certain n will pass through this ball. That's what they must intersect it, and if they intersect it, then in particular they pass through the boundary of it. So I have curves that are all passing through the boundary of this, and now this boundary is the boundary of a sphere, and a sphere is compact. Okay, so I have infinitely many points where these curves are hitting the boundary, so that infinite set of points must accumulate to a point that's also on the boundary. Okay, so starting with R, I've managed to define a new point R prime that's also a convergence point. So far, just one new point. I started with R, I drew this Euclidean ball, and since these curves all pass through the boundary of this ball, and since the ball is compact, they accumulate to a point by sequential compactness, and that's that point. Okay, so I haven't done much. I've shown that given one convergence point, there's another convergence point. Okay, now what I do is I take these balls and I take successive ones that are smaller and smaller in a sequence of rational radius balls, and rational numbers being dense in the reals, I can actually make this intersection point travel closer and closer to R. So I've made this finite piece of my convergence curve. Okay, so first I take a ball of radius r, then I take a family of balls which are smaller and smaller, an infinite such family, and this point that I've been able to define r prime will now move closer and closer to r, and in the limit I have an entire line segment from r to r prime on which every point is a convergence point. Now I start with r prime, define a new ball, and I can extend this, and by doing this I can extend this indefinitely. So this is Garrosh/Wald's proof of this theorem, which says that given a convergence point, there's an entire convergence curve through that point. Good. Okay. And now we have everything that we need for our main theorem, which is the compactness of the space of curves from P to Q. And this is fiendishly clever, and it's just very cute. So here we have P, here we have Q. Note that here we are focusing on curves with endpoints. We are not saying they are inextendable. One more, by the way, point to note is that nowhere did I use the Cauchy property, but now I'll use it. I have to use the fact that the spacetime is globally hyperbolic, because the theorem I'm now trying to prove that the space of curves from P to Q, causal curves, is compact, and that's an equivalent definition of global hyperbolicity. So I must use the original definition, Garrosh definition, which is that every inextendable curve passes through a Cauchy hypersurface. But I don't even have any inextendable curve here as yet. Okay, so the first thing I do is to delete the point Q from my manifold. Now these are all inextendable. So I have an infinite family of inextendable curves. Now unquestionably they all pass through P, because my family all started at P. So P is definitely a convergence point. But I've argued that given a convergence point, I can reconstruct a convergence curve. So far so good. The problem now is what happens when I put back my point Q. So here's a convergence curve, and it approaches this missing point Q arbitrarily close, because it's a convergence curve of curves that all do the same thing. Now I put back Q. Okay. Now my original family of curves all terminates at Q. That's how I defined them. What does the convergence curve do? It has two options. It can either terminate at Q at the same point, or become inextendable, or remain inextendable, I should say, remain inextendable. Right? If it terminates at Q, it becomes extendable because it has an endpoint, and that's the endpoint. But it also has the option to remain inextendable because it's a limit of things, and we don't know whether the limit shares that property of being inextendable or terminating at Q with the original family. Okay. Now I want to argue the last point, which is that 2 is out, because if this curve is inextendable, and if I have a Cauchy hypersurface here, then this inextendable curve isn't going to pass through the Cauchy hypersurface. But then that's not a Cauchy hypersurface, and my spacetime isn't globally hyperbolic. Okay, so if 2 is true, then the convergence curve does not pass through sigma, but is inextendable, which is a contradiction with global hyperbolicity. Because global hyperbolicity says that every inextendable curve better pass through the Cauchy surface. And in this example, I took both P and Q to the past of the Cauchy hypersurface, with Q in the causal future of P. So by invoking global hyperbolicity, I've even proved that the convergence curve terminates at Q, and that means every infinite sequence of causal curves has a causal curve which is its convergence curve. So the space is sequentially compact. There's a little bit of stuff about it also being second countable, but I convinced myself that that's trivially true, so we needn't go into it. Sequentially compact is the same as compact. So we learn from all this that CPQ is compact. So I won't keep writing what this space is. It's the space of causal curves from P to a point Q in its future. And that's all it is. It's just a space of causal curves. Good. Now, there's one more theorem, but I think we might get very bored going into that, which is the compactness of the causal diamond. So what I'll do is I'll postpone it till the time when I need it. If I need it, then I'll prove it then. It's simpler than this, but it's just one more thing. But there's one theorem that's absolutely essential, and this is the big theorem of the day. In a globally hyperbolic space-time, there is a unique time-like geodesic of maximal proper time between P and Q. I'm going to always assume that Q is in the causal future of P. So there's a unique time-like geodesic of maximal proper time, and this is a direct consequence of this theorem, and I'll show you in a second why. Okay, this is the reason why we did everything we've done for the last 25 minutes to prove this theorem. Okay, so now we are finally focusing on geodesics and their proper time. Okay, and here we've, in fact, in all of this discussion, we've actually had Q being not just in the causal future of P, but in the chronological future, so that there are time-like curves, because we just want a theorem involving time-like curves. Okay, so step one in proving this is try to make a family of curves of causal, inextendable, etc., that have an increasing proper time without limit. So if the tau n, so tau n here is my label for the total proper time of a curve, and I'm going to assume that each of these curves has a total proper time that's just getting bigger and bigger. Okay. Now, if the proper time is getting bigger and bigger, then there's no way that this family can tend to a convergence curve, because the proper time has no limit. Okay, so it's an increasing curves that have an increasing proper times tau n, so no limiting proper time. This implies that there cannot be a convergence curve. Right, because if there was a convergence curve, it would have some proper time. But since I've taken my family to have increasing sequence of proper times with no limit, then the convergence curve can't exist. But this is a contradiction with compactness of CPQ. This contradicts compactness of CPQ. You cannot have a family of causal curves that have increasing from one given point to another given point that have proper times increasing without limit. Not possible. If that's not possible, then there has to be an upper bound. Hence, there's an upper bound of the proper time. proper time of this family, say tau bar. Good. So we take the least upper bound and we'll call it tau bar. Good. Now take a family where the proper times, next consider a family of curves whose proper time tends to this value. Tau n tends to tau bar. So it has a limiting proper time, tau bar. So whose proper times converge to this value. Okay. But now because of compactness of CPQ, there must be an actual curve whose proper time is actually this. And that's the result. So compactness of CPQ there must be a curve which, like all the curves in this series, is causal and inextendable. Of maximum proper time equals that value. Okay, so this is the statement that the family converges and the convergence curve has a fixed proper time. But now that I found a curve of maximal proper time, it has to be a geodesic. We discussed last time that curves can locally maximize or they could even locally minimize proper time. They would still technically be geodesics. But here we've said that it globally, over all possible curves, it's the one that maximizes the proper time. And there's just one and it has to exist. But it only exists because of compactness of the space of curves from P to Q, and that only holds because our space-time is globally hyperbolic. So this is the key theorem, and now I can write essentially in Hawking's own words what's his theorem, his first theorem, and you will see that there's nothing left to prove. Okay. So we consider a global, so this is the theorem, Hawking. In my notes I've referenced Wald, where you'll find a very precise statement of it. Consider a globally hyperbolic space-time satisfying the strong energy condition, because now we are going to use Raychaudhuri's equations. On a given Cauchy hypersurface, sigma, let the expansion theta be greater than 0 everywhere and bounded below by some value. So we are allowing theta certainly to vary over this surface by some constant c which is positive. Okay. Rest of the theorem here. Then all past directed time-like geodesics focus by a time t focal, which I defined earlier, which is actually minus d minus 1 upon c, this constant. And the space-time is geodesically incomplete. In pictures, here's my Cauchy surface sigma. My geodesics, as per Raychaudhuri's equation and as per the diagram I drew earlier, are all focusing in a time that is in magnitude less than or equal to the d minus 1 over this constant. This constant is the minimum theta 0 on that surface. Okay. Now I'm here. I try to make a geodesic from here that goes here. I can't, because if I run that geodesic backwards from here by this Raychaudhuri equation, it has already focused here, and by the analysis we did last time, after it focuses, it's no longer a geodesic. Okay, so I can't make a geodesic that starts here and hits sigma. Now I have two options. Either I say, well, that means geodesics from here don't hit sigma, then space-time is not globally hyperbolic. Or I can say there are no points here. This part of the past doesn't exist. It's not part of my manifold. Hawking and Penrose use the word singularity for that statement. Modern treatments use the term geodesically incomplete. There are all kinds of statements ranging from polite to quite strong about the inappropriateness of using singularity. If you want to see the most amusing one, it's by Kerr of the Kerr metric, I think 2023 December. It's on the archive. And he wrote about what a fraud this whole singularity business is, because they never prove anything is singular, they only prove that space-time is geodesically incomplete. The community's reaction seems to be, yes, we always knew that. So I think we should break for tea. Happy to take questions now or during tea. So I hope it was clear that the global hyperbolic nature was important to establish that something shouldn't exist over here. Because if it existed, there should be a geodesic going there, but there isn't by Raychaudhuri equation. So it's the last nail in the Raychaudhuri equation theorem which really proves that it's a theorem about space-time and not just about a coordinate system. Yeah. Good. So I think this is a good time to take any questions you might have about this part. This is a sort of self-contained discussion, everything I did last time and this morning. No, so Hawking singularity theorem is not about black holes. Now we are going to talk about black holes for the rest of today and next lecture. That is Penrose singularity theorem, different guy. Yeah. In fact, which was first actually, which was before Hawking. He kind of got some of his ideas, I think, from it. But the key difference is that when we talk of black holes, we need to talk about null geodesics, because we are always talking about what light does. And here, because we are talking about cosmology, this is really a cosmological theorem which says, which is trying to justify that there was a Big Bang. Basically, we don't use those words now in polite society, but that's what this is trying to say, that there's a Big Bang. So Big Bang is in the time-like past, but black hole singularity is somehow in the null future. So everything will be null from now on. So that's what I'm going to now. And in fact, once we get to that subject, then it dovetails to another subject, which is black hole thermodynamics, Hawking's area increase theorem, entropy of black holes, Hawking radiation. It all that's the whole next topic, but not for my lectures.
If a massive cell really collapses to form a black hole, can
Yes.
we apply this thing and like in the like time like future or
Well, the massive shell may collapse to form a black hole, but the black hole diagnostic is how is light behaving near a black hole, just outside and just inside. And so we really want to know about null trajectories. In some sense, I would say the difference, of course, even in our past, light obviously comes from the past of us. But we really want to know how matter of the universe sort of expanded from whether it expanded from a Big Bang. And this is sort of the most rigorous statement that the past is geodesically incomplete as long as theta 0 is positive and bounded below on this. Last time, by the way, I mentioned that theta can be identified up to a constant with the Hubble constant, but it's a local Hubble constant. So it's allowed to vary everywhere, but it should be always positive. Now, if you allow it to be positive somewhere and negative somewhere, you don't get any of these results. And Hawking had issue with that because his point was there's no hope that we can travel all over the Cauchy surface and find out the Hubble constant everywhere. So he had other theorems, but I think if I start going on to Hawking's other theorems, that will take the rest of. So now, yeah, any other questions, comments, questions? So now we are going to talk about everything null. And it's a very fascinating subject. And the the first goal is to derive something called the null Raychaudhuri equation. So I like to claim that Amal Raychaudhuri had a younger brother called Null Raychaudhuri who found this other equation. And it's really actually, this is in a way too generous an attribution. It is actually due to Sachs a few years later. And Raychaudhuri in interviews always said, you know, I actually derived the wrong equation. I derived the time-like version of the equation, but what all these fancy people in Cambridge and Oxford need is the null equation, which I never derived. So it's actually not his equation, but this is the name that has stuck. Good. So now what can we say about this? And here we face one of the, so we'll start by talking about null geodesics. And here we face a difficulty that's really conceptual, physical, and very beautiful, which is how do you compare one geodesic to another? With a time-like geodesic, we could say that geodesic keeps maximizes proper time. But with a null geodesic or with any null curve, proper time is 0 by definition. So how do we even compare one with another? And there's a beautiful answer to that in the literature. I'm not sure where it started, but Witten spends quite some time on it, which is a physics proof that such an issue actually exists, and I find it very mind-boggling every time I think of it. There's a phenomenon called gravitational lensing, and that means we have a source here, and it's shooting out light rays, and we are here, and there's some galaxies and matter distribution, and the light rays are bending because of the gravitational influence of these things, and they're reaching us, but they reach us at different times in our time frame. That means, but they're all null geodesics. They're not under the influence of any acceleration other than that due to gravity, and we all know that in gravity, space-time is curved and everything follows a geodesic, and light in particular follows a null geodesic. So if the light is bending, it's in this interpretation, geometric interpretation, it's bending because that's the path of a null geodesic locally. And it might be that light doesn't want to go through certain trajectories because they are not null, and so there might be regions where you have a nice null geodesic and it picks that in some sense, following this Huygens principle way of thinking. But the end point is that you get light from different from the same source, so it started at the same time and on different trajectories, and some are better than others. One of them reaches you before the other one. That's amazing, and we need to formalize that. Now, there's a long history of how to formalize that. Probably much of this was again Sachs, who I mentioned, and then Penrose. But Witten actually seems to have proposed a new idea. At least I haven't been able to find it anywhere else in the literature. And this is from his lecture notes of about 5 or 6 years ago in New Zealand, I think. And it's called promptness. And it's very geometrically appealing. A diagnostic for null geodesics. And what is it supposed to diagnose? It's supposed to tell us which one among many from the same place to the same place is in some sense the best one. Okay, and it's the analog of maximizing proper time for a time-like geodesic. Good. So let's right away get, it turns out of course that his construction is equivalent to some other properties which were known before, but it's just very intuitive. So first I'll write the definition and then I'll draw a picture. So a causal path. So now we are not going to say that Q is in the time-like future of P, it's in the causal future, so it could be time-like or null separated. We'll allow everything to be null separated. A causal path from P to Q is prompt if no other causal path well, if there is no other causal path that reaches the spatial location of Q at an earlier time. Sorry. So this is actually a coordinate dependent definition, and something I've been discussing with a colleague is whether this can perhaps be made coordinate independent. But let's draw it and then you'll see what I'm saying. So here's P, here's Q, and here's a causal path. By the way, nothing has been called, nothing is null so far, it's just causal. So here's a causal path, and here's another causal path. And the important thing is that this is vertically below that, which means in terms of time that it reached, because this is the same spatial point. So this spatial point is the same for this Q prime and Q. It's only the time value that differs between Q prime and Q. So if there's a path from P and P to Q and another path from P to Q prime just under Q, then the original path PQ is non-prompt. So this is a case where this is non-prompt. But if no path from P to Q prime of the kind I've drawn exists, then this path is prompt. And the thing that is getting used to is something I emphasized right at the beginning on Thursday, which is that it's a space-time diagram. So a path from here to here and from here to here is ending in the same place. It's the same spatial point. It's just not the same time that it's reaching there, but it's exactly the same spatial point. And so we can talk about comparing in some sense who got there first. It's also something that we need to get used to, that if you're under someone else, then you have actually got there first. Under in this picture is below, but it actually means you got there first. So we have to keep this in mind throughout. Okay.
Can one do this as like extremizing the retarded time at least in because this space is for like retarded times t minus r say measures?
Yeah, that might be true. It might be. No, t minus r. Oh, I see. T minus r. Is that a null coordinate in your?
Yeah. So t
But then how can? That's the whole point. You can't extremize a null coordinate because it's null. So what do you extremize? What is the? There should be some quantity that you extremize.
like if the spacetime is paired, then I know that t minus r between 2 points which are like connected by null line is 0. But when there is a gravitational field, then like suppose this gravitational lensing or whatever happens.
Yes.
So now t minus r will be some positive quantity, something like that. Now you can just claim that like I want to find the path between two of the points where t minus r is minimum. Say.
No, but the problem is I might find more than one. And t minus r will be, so light will in fact do what you are saying, but it might do it in more than one way. That's why we have gravitational, and that's what that diagram is saying. So this path might have t minus r non-zero, but this and this and this all have t minus r 0. So they are all null. But then we still haven't found out which one is sort of the best. And so promptness is the, yeah, so this is the definition. Yes.
Once you have null geodesics, then you do have a notion of affine parameters.
You have an affine parameter, but it's very much up to you, unfortunately. That's the problem. It's difficult to compare if two people have different affine parameters because you can scale. You can scale your affine parameter or shift its origin. So it's difficult to compare two paths in an absolute sense.
Is there not some sort of normalization that allows you?
No, that's exactly the point, because the norm of the null vector is 0. So now you could of course, this is a problem with it's a problem with Lorentzian-signature, because right, the standard statement is okay, you have a null coordinate, let's say in Minkowski, you have u and v, both are null, and u dot v is, let's say, 1. Now you think that's a normalization, but I can scale u up and v down, and u dot v is still 1. So it's really frustrating to try and normalize anything null. And that's somehow what this comes from. But I emphasize, this is from a few years ago, this definition, and obviously Penrose didn't need it to prove his theorem in 1963 or 4. So he had something that was a proxy for this, and I'll tell you what it is in a minute. But I find this very, very appealing. And yeah. Now, we've not introduced any null or geodesic concept here, but we will see. So let's have a little preview that a prompt path will always be a null geodesic. In some sense, this is the analog of a statement I made earlier about time-like paths. If you have a time-like path that maximizes proper time, it has to be a geodesic. You don't need to check it for being a geodesic. Here, if you have a path that is prompt, that means there's nothing which can get there earlier, then it has to be null and a geodesic. Okay, but the reverse is not true. Every null geodesic is not prompt. So you can use promptness to distinguish null geodesics from non-null geodesics, as well as null geodesics from each other. And it's the latter which is more important. Yeah. Okay. We could use words like saying P to Q prime is a more prompt path than P to Q, but this diagram doesn't show that P to Q prime is prompt, because there might be some other path which gets there even earlier. So you can grade them in order of promptness, but the one that's the earliest to get there is the one that's really prompt. Okay.
And is that a Riemann sequence then? I mean,
Is that?
this problem we were just talking about with that one parameters.
Yes.
Is it now clear that there's a clear notion of relative promptness?
Yes, I think there is a clear notion of relative promptness, but unfortunately, at least in all of Witten's discussions, it's tied to a choice of coordinate system, because what's exactly under is not is defined by what your time axis is. But so I've been talking to a colleague, as I said, at IISER Pune, and we think that this can be extended to light cones and make it a causal arrangement in causal order. And already we'll see that there are some invariant properties, that is coordinate invariant properties of prompt paths, and I'll actually tell you one right now. So theorem, a prompt path okay, yeah, path from. So it's always difficult to write from where to where, because you see these are space-time points. So yeah, I could say P to, okay, if it's prompt, then I can say it's from P to Q and there's no other such path. But if it's non-prompt, then I'm comparing paths which have different endpoints in space-time. Sorry if I keep saying this, but I'm constantly confused by this fact. Okay, a prompt path if there is a prompt path from P to Q, then Q must lie in the boundary of the causal future of P. So I discussed causal future last time, and for Minkowski it's very easy. This is the point P, and the causal future is called J plus of P, and it includes everything in this future light cone as well as the light cone itself, which is the boundary. But the actual boundary is just this, rotated of course, and so that's del J plus of P. And the statement is that if there's a prompt path to some space-time point Q, then Q better lie on the boundary of the causal future. So Q must be here. In Minkowski, it's very obvious, because if Q were here, then there's no way this could be prompt, because I would simply come down here and have a much prompter path from here to here. So in Minkowski, it's trivial. But in a general space-time, you can still argue by topology essentially that a prompt path existing from P to Q means Q has to lie in the boundary of the future, so lies on the future light cone. Good. Now there's a very nice model of how non-prompt geodesics can arise even if the space-time is flat. You see, it's difficult to make concrete models to illustrate things we say, because often these models will require a space-time metric that's pretty bad and you have to do a lot of calculation. But here's a very nice model. We simply take effectively 1 plus 1D space-time, where space is a circle. So it's S1 cross R. So this is time, which is on R, and this is space, which is valued on a circle. And a lot of interesting and things happen, and we can learn a lot about promptness and also more generally from this figure. So let me start by marking my original point P, which I will not change here. Let's now ask what is the future causal future of P. Well, for that we'll need to send out a light cone, but then of course this is a circle, so this continues behind, so like this. And so bad drawing, but you get what I mean there. Okay. Now let's start looking for a null, for a prompt path. So if I go from P to P prime, which is here on this light cone, then of course this is prompt. Everything is, at this point the system doesn't realize that it's on a compact manifold. We've just gone a short distance from P to P prime, and this is prompt. And it satisfies everything. There's no point below it in the causal future of P, so there's no hope to get here faster. Good. However, we notice an interesting thing happens at Q. At Q, the null path from here to there and the one from here to there meet. So it's a focal point of null geodesics. And now supposing we wanted to go somewhere that's beyond that focal point, for example, Q prime. So this is very similar to the discussion on focusing of ordinary time-like geodesics, which we did last time, except we are doing it for null geodesics. What we argued with time-like was that whenever there's a focal point and you go beyond it, then there's a smoothing argument which tells you that whatever your geodesic appeared to be fails to be a geodesic after you cross the focal point. But here we can't test that because everything is null. All my lines are at 45 degrees and they're all null. So it takes me zero proper time to get here, whether I go this way or I go that way. But there's something else now I can do, which is that I can go here and stop. Okay? And this path is a null geodesic like all others, but it's exactly in the past of Q prime, and so I've got to the same place as Q prime much earlier, and so the original one was not prompt. Okay, so this is a lesson we learn that, so in this example we see that beyond a focal point, and this gives us hope that the whole concept of focal point will transport to the study of null geodesics. Prompt path is no longer prompt. So what was prompt up to the focal point is no longer prompt. That's the key idea. Okay. There's also one more interesting diagnostic. You see that Q prime fails to be in the boundary of the causal future, because the causal future here is a weird thing. It has this boundary and it has this boundary, but at this point the boundary runs out, but the bulk is still there. So everything in the upper part of the cylinder till infinity is obviously in the causal future of P, but it has no boundary. Like here, there's no boundary on the sides of this. It's just a cylinder. It's just periodically compactified. So there's no boundary. So the boundary is only this kind of thing which sort of holds it up. So you could shade everything above these two lines and it's all in the causal future of P. But Q prime in particular does not lie on the boundary. While any point before this focal point, whether it's here or here or here or here, does lie on the boundary, and then my geodesic is prompt. So you see that focal point failure of geodesic to be prompt beyond it, failure of a point beyond it to lie on the boundary of the causal future, all are linked in this example. Now we have to formalize it to be more general. So there are a bunch of cute theorems. And these I think are all due to Witten. An initially non-prompt geodesic cannot become prompt. This is sort of again trivial in simple examples like Minkowski. If I'm lazy and I'm not traveling at the speed of light for a while, and then I suddenly become enthusiastic and try to speed up, I'm never going to match another person who was traveling at the speed of light from the beginning. And so that in a diagram is basically, this is my non-prompt path, and I'm trying to become prompt, which means that I want to reach a point here, and that's hopeless because the only way I can reach that path, having been non-prompt for a while, is to suddenly speed up. Of course, this is not again a very useful example because this one is time-like. So if it's time-like, it's obviously not prompt and it's obviously slower than a null path. But we want this kind of criterion to be used to distinguish different null paths. So if any of the null paths is non-prompt for a while, it's not going to manage to be prompt later. So let's see how we prove that. So this is what I call Witten's shadowing argument. So here we now don't say we are in Minkowski anymore, we are just in some space-time. And there's a path to a point P2, but it's non-prompt initially, which means there's another path to P2 prime just under it. Now, the key idea here is that we are under it, which means we are already there first. Now, whatever this does, we simply shadow it by remaining below. So when it gets to another point Q2, I've still got there first. This is the sort of idea to show that the initial part, or if the initial part is non-prompt, there's no hope of the whole thing being prompt. If you can get here sooner than that guy, then you can also get here sooner than that. So it's I call this shadowing argument. We use this repeatedly. But while shadowing in the picture looks like I'm below, it actually means I'm earlier. Okay. A converse sort of result, a path that is initially prompt can become non-prompt later. And that's easy to draw. So here's my P. Here I am very prompt, but for some reason at this point I lose energy and I slow down. That's perfectly all right. So here I was prompt, which means there was no path which was getting to this point before me. But at this point, I for some reason decided to be non-prompt. I shouldn't have used the word slow down. And then there can be a path that's more prompt, or that is prompt. Again, I emphasize that these drawings are a little trivial because we are drawing things in, the only thing we can really draw easily is Minkowski, and This is actually slowing down literally because it's time-like. But these theorems apply to more general situations where plausibly both of these are null, but this is less prompt than this one. And that's exactly the kind of problem that we anticipate, which is why we need to compare null geodesics in the first place. Okay. Now there are proofs of these things, but I think it will be really tedious to go through them here. But I'll just state a theorem associated to this left scenario. Again, Witten. Every non-prompt, so this is very non-trivial theorem. Every non-prompt null geodesic has an initial part which is prompt. And the easiest way to believe this is to remember my example of gravitational lensing. You see, imagine this is my light source, this is me, and this is some part of the universe that's vacuum. And then here are all my galaxies, just as a sort of model. It emits into a vacuum, into empty space, and then eventually passes through a bunch of galaxies. Well, here, everybody is going to be prompt. They're all going off in their different directions. But in vacuum, they're just not experiencing any gravitational field, nothing to choose between them. They're all prompt. Okay, but then depending on what they experience when they go through matter, they will end up, one of them will win the race and the others will become non-prompt. So that's this theorem. I think this physics argument that this physics argument seems to me a very good plausibility argument for this result. And now we consider focal points, but with a twist. So now we've shown one example of a focal point. Now let's write down the general theory of focal points. And for that, we'll draw a diagram very similar to something I had last time, except that last time in our minds everything was time-like and now everything is null. So here's my starting point and here's my focal point. So gamma is a null geodesic and gamma prime is another one, and they both reach P2, and that's where they focus. Okay. Now the question is, continuing gamma to P3, am I still prompt? Supposing gamma from P1 to P2 was prompt and I continue it to P3, does it continue to be prompt? Okay. Now, once there's a focal point, we have one part of the old argument still true, which is that this path has a kink. And last time we realized that kinks are bad for proper time. They always make your proper time less than it should be, which you're trying to maximize. But now we are going to do something different. Earlier, if you remember, we tried to smooth over the kink like that, but still reach the same endpoint. Now we are going to do something different. We are going to say, well, the kink tells us that there must be a path which doesn't hit the kink and ends up just under P3, which means it's more prompt. So now Witten gave these kind of intuitive, so I'm always referring to Witten's preprint light rays, singularities and all that, which is, I've given some set of references and it's in that set. So he gives this sort of argument pictorially in the main body of his review, but there's an appendix called More on Promptness, which has quite rigorous details. I think I'll just wear you out if I go into those details. but um, so this says that a focal point renders a null geodesic non-prompt. Assuming if it was prompt to start with and it thought it was doing very well up to here, by the time it continues past its focal point and reached here, is disappointed to find that there was a more prompt geodesic that was found by smoothing around the kink and then not trying to join that, but just continue as fast as you can and get to the end as fast as you can. Okay, and I'll stop in 5 minutes. I think that should be 5 or 7 minutes. Okay, now, yes, yes.
It's supposed to be for every non-geodesic, or is there one that can be special and escape this?
No, so if there's a focal point, then the null geodesic that experiences the focal point cannot then be prompt once that's happened. So it's the same recipe. Focal point equals disaster. For a time-like geodesic, let's start with a spatial geodesic in ordinary Riemannian geometry. The moment it encounters a focal point, which means another geodesic comes and collides, it's never going to minimize distance beyond that. It's just, that's not the way to go anymore to minimize distance. Okay, then for the time-like case, the moment there's a focal point, that's the Raychaudhuri case we discussed, then going beyond it, you'll never be able to maximize proper time. And here, if there's a focal point, then continuing beyond that focal point, you'll never be able to be prompt.
So what is the statement about the prompter geodesics, which makes this one non-prompt? Do they not have a focal point?
Yeah, this doesn't have a focal point. That's of course also what we did in the previous case. In the time-like case, we smoothed this kink so that the focal point went away. And then we said, well, that has actually a better chance to maximize proper time. Here, we also smooth it, but we don't try to join there because we are not interested in reaching there, a space-time point. We are interested in reaching just the same space point, but sooner. So it's all the same ideology. And by the way, the smoothing ideology for the time-like case originated with Penrose, who called it a crude argument. But now that Wald and Witten have certified it, I think we can call it a widely accepted argument.
So in this picture, there even at the initial, like when we are drawing, like going from P1 to P2 by a null line, that was also not prompt.
No, this is prompt. This is prompt up to P2.
But now in the below curve,
Yeah.
I can draw a point below P2 and I can follow the
Yeah.
same path.
I see. Good point. Sorry. I think I might have said something wrong. This is bothering me a bit. Give me a second to figure this out. Yeah, what you're saying is that this curve was always more prompt than that. So that was never prompt.
Yeah.
But somehow this should not be the right argument. I'll have to think about this. Let's talk about this at over pizza, and maybe I'll make it a little more precise next time. It might be that actually what you have to do is to follow this most of the way and sort of but this is very qualitative. Yeah, I think this is important to clarify. Okay, we'll come back to this claim that a focal point renders a curve non-prompt. And yeah, the last thing is a theorem. I'm smelling pizza. I cannot lecture when I'm smelling pizza. Yes. So let me put this out there and I'll give you the proof next time on Thursday, and we'll take off from there. Thursday will be all about null geodesics and their role in Penrose's Singularity Theorem, which is essentially the statement of closed trapped surfaces, which is the statement that got him a Nobel Prize. So, achronality means there are no 2 points on my curve that can be connected by a time-like curve. And it's obvious in one way. I mean, if you have a prompt path, you don't expect there to also be a time-like curve that connects 2 points on it. But in fact, it's the other way also. If there's never a time-like curve connecting 2 points, then it is achronal. And in fact, one exercise is that you can look at that cylinder picture where there's a curve that becomes non-prompt after a focal point, and there you can actually see clearly that it also fails to be achronal at that point. Okay, more on Thursday if you still have the energy.
Pizza actually is delayed.
Sorry?
Pizza is
Pizza is delayed. Then what was I smelling? I mean, it's all in my mind. No, someone else is having pizza. I can smell it. Let's go and take their pizza. Anyway, I think this is a good break point because it sets the stage for the final discussions.